Welcome back. Today we'll look at paper 1 variant 12 of the October-November 2023 series. Now, as always, this paper is 1 hour 45, and if this video goes on too long, then I would recommend watching it, maybe 1.25 or 1.5 speed, okay, if it's still understandable. I would also say, make sure to also check the mark scheme, because, some questions maybe I'll give like 2 or 3 answers, but maybe the mark scheme might have 5 or 6 answers, okay? So this video, it's supposed to be just kind of an extra explanation for some of the questions, because I know sometimes, students, they look at the mark scheme, right, they just see the answer, but they don't actually know why that's the answer, right? So in this video, I'll try to actually explain in more detail, but I would say, also use the mark scheme as well. Definitely don't just rely on these videos. Right, anyway then, jumping in, question 1 says, malware can be used to corrupt data stored on the computer. Tick one box to show which cybersecurity threat is not a type of malware. Right, so let's just talk about what each of these are then. So phishing, basically this would be either by sending emails, maybe SMS, right, it could be a phone call, it could be like a social media message, right, I've got a few of these on Discord recently, and usually this will include some kind of link, and of course you'll then click the link, and when you visit that website, that website might have, let's say, like a fake login page, or some like custom order page, something like that, right? And they'll try to get you to type in, let's say your username, your password, maybe your email, right, credit card number, telephone, right, any sort of personal details. And then I guess actually really that second stage is actually called pharming, all right? So there's 2 types that are often used together, phishing and pharming. And the way I like to think of it is, if you think a fisherman, right, you're going to have the fishing rod, right, of course then you have the hook on the end, obviously used to sort of catch the fish. So you say, phishing, what you're doing is basically you're trying to reel in, kind of potential victims, right? You're trying to trick people, into taking the bait, which I guess, with a phishing example, that's like the worm or something. Right, and then, so when you've sort of reeled them in, when you've got them hooked, then what you do is, then you have to do the pharming. And the pharming, right, that's PH like this. Right, pharming. And the reason it's called pharming is because, whereas, sort of real life farming, right, agriculture, you would obviously be growing crops, right, growing food. Now, in this case, right, this farming, what you're doing is you're growing your list of stolen credentials. And again, that's right, stolen usernames, passwords, credit card numbers, right, emails, etc. So, maybe we just know, right, but actually these then would be types of social engineering. Phishing especially, right, that's going to be social engineering, because what you're doing is you're basically kind of taking advantage of, maybe you can say, the user's kind of naivety, or taking advantage of the user's trustworthy nature, in order to exploit them, right? So this is social engineering, not malware. If we just quickly talk about the others, so ransomware, what this is it's going to be malware, which obviously you kind of unexpectedly download onto your computer. It's then going to encrypt all of your files, and it will then, then it will ask for a ransom. Okay, so if you don't know, a ransom, if we're talking about real life crime, right, maybe someone kidnaps someone or, holds them hostage, and they'll say, like, give us money, okay, then we'll release the hostages, give us money, or, we'll release the, we'll release the kidnapped person. So it's kind of the same, where basically they're going to encrypt all of your files, right, so your computer then becomes unusable, all of your files just gone, basically. Not gone, but, you can't really open them, right, they're all corrupted. So then what you'd have to do is you'd have to pay them the money in order for them to give you the decryption key. Now, the problem is sometimes even if you pay them the money, right, they still won't give you the decryption key, because, maybe they don't have it themselves, right, because, maybe their malware is not that sophisticated, it doesn't actually send anything to the server. Or it could just be without, I don't know, they're just trying to, like, troll you or something, and, even if you pay the money, right, they're still not going to give you the key, just for a joke. However, actually, in most ransomware cases, they would actually give you the key, because, from their point of view, if they get a reputation where people are like, hang on, we pay them the money and they still don't give us the key, then of course future people are definitely not going to give them the money. Whereas if people are confident, actually, like previous examples, people have paid and have gotten the key, right, hence they've been able to decrypt their files, then yeah, obviously that's good for, the ransomware gang's reputation, which is, yeah, kind of ironic to say. Right, so the next one then, virus, I mean, this is just where, again, it's going to be a type of malware that's going to infect, one file, and then it's just going to spread, on your computer. And I mean, the reason for that is, of course, why it's good to have multiple backups of itself, because if one gets detected, and, maybe deleted by the antivirus, anti-malware, then, of course, it's copied itself like hundreds of times, right, all over your computer. And I mean, this really is just like a biological virus where, of course, yeah, you get infected with one cell, right? That cell then, divides, it replicates, it spreads, right? So that's what a virus is. Right, and then the final one, worm. I think the best way to do this with a diagram. So let's say this is computer 1, right? This is, computer 2. Well, let's say if this computer gets infected, right? What a worm is going to do is going to travel from this computer, right, and then it's going to reappear on this other computer, okay, and you can kind of think of this like in the ground, right? Maybe a worm can, sort of travel into the ground, right, and then of course it's going to, reappear somewhere else in the ground, kind of like that whack-a-mole, arcade game. And I mean, that's basically the same thing here, right? So a worm will appear on one device in the network, and then, then it will spread to another device on the network, right? So it just, tries to infect everything on the whole network. Now, this could be just on a local network, right? But it could also be, on a, sort of on a WAN, right? It could also be on the entire internet, which we've seen before with things like WannaCry. So yeah, WannaCry was a fairly recent worm, maybe 6-7 years ago. But there's also been various like kind of email worms, which are basically, like they would include an attachment as an kind of as an email, and it will say, download this, because, well, yeah, again, there'd be some sort of social engineering involved. I think one of them was called like Love Letter, and then there's various other ones. Of course, people then click on this file like, out of curiosity, right? That then infects their system, and then it sends an email to all of their contacts, right? So you can see how this is kind of exponential, because if one person, downloads the worm, it then sends it to 100 of their email contacts, right? If one of them, opens it, again, it sends it to 100 of their email contacts. All right, but then if we want to talk about one other example, I mean, I guess there's a few, right? So we could talk about spyware. And what spyware will do is, well, as the name suggests, spy, right? It's going to try to steal all of your personal information. And again, that could be usernames, passwords, credit card numbers, right? Maybe social security numbers. Any kind of like identity theft, basically. We could also mention something like adware. So adware is where they're just going to, bombard you with adverts. And of course, like the developers of this adware are going to get, the advertising revenue. And then I guess the next one probably is just a trojan. And of course, here we do only have to list one, right? But just to list all of the examples, you could probably say. And I mean, a trojan, I mean, yeah, maybe the original story, like the Trojan horse, which I think is it from Troy or Sparta? Yeah, I'm not really sure. But basically, this is where, let's say you have a normal file. And I mean, this will usually be some reputable file like, Microsoft Office or Chrome, something that lots of people want to download. So let's say here you have, the legitimate file, right, is safe. But then what they'll do is they'll also add on like an extra bit of malicious code. And so this time, like, people will get like Microsoft Office, right? They'll think it's legitimate because, maybe someone said, hey, here's a free version, right? They've downloaded it. But of course, because the hacker has included this extra bit of malicious code, well, now their system is going to be infected. And one way to prevent this, and I think usually they don't mention for IG, but if anyone's interested, one way you can prevent this is just by hashing the file, right? So a lot of websites, when they have a download, they'll also have a hash, which often will be like an MD5, maybe also like a SHA-256, right? These are just different hashing algorithms. And this will just be some long code, like maybe A7B, 4, right? Some random code. Because what this does is, well, the developers of this file, right? So the original software, right? The clean software, they'll then hash that file, and they'll say, well, the legitimate version of the software has this hash, right? So then when the user downloads it, right? The user can then hash the version they downloaded. And if their hash is not equal to this, well, then they know that the version they've downloaded is not the original version. And yet either that could be because it's been modified, say, by a trojan, right? Or it could also be some, corruption issue when they were downloading. Yeah, maybe some of the, well, I don't know, maybe when they were saving the file, they had some hardware error. Yeah, it could be some network error, right, that's caused some corruption. But of course, in that case, they can just re-download the file, make sure to get the original, right, the clean version. Right, so then we want to say the type of software that is used to find and remove malware from a computer. Now, I would say, just regular people, they would often just call this antivirus. But here, because it's specifically saying malware, yeah, I guess really you want to say anti-malware. Because obviously, well, the idea is that anti-malware is going to remove all types of malware. Whereas in theory, if something was just an antivirus, I suppose technically it would only be, removing viruses, right, and possibly not removing, say, ransomware or spyware, yeah, or trojans. But again, in common usage, people just say antivirus for everything. But I guess the technical one, the Cambridge one, right, they actually want you to say the more generalized anti-malware. Right, the next one, so a register stores the binary number. Okay, this gives the denary for this binary number stored in the register. Now, here they don't mention if it's signed or unsigned, so by default we can consider this unsigned, right, it's going to be positive. So here then we just want to add all these together. So, right, the first one is going to be 128, okay, the next one is going to be 64, right, the next one is going to be 32, right, then, well, so no 16s, no 8s, no 4s, right, then 2 and a 1. So yeah, I think I don't really have much space here. But right, so 8 and 4, that's going to be 12, right, plus 2, 14, right, 16, 17. Right, then we get a carry of 1. So that's going to be 3, 9, right, that's 12. And then again we get a carry of 1, okay, 1 and 1, right, is 2. So yeah, I think this should be 227. Right, then we want to give the hexadecimal number for this binary stored in the register. And the way we can do that again is if we just separate this here. So, I mean, we just separate binary into groups of 4. Right, so here we've got the first 4 bits, then the last 4 bits. And as we can see, well, this is going to be 14. Okay, so 14 in hexadecimal is going to be E. And I mean, the reason for that, I mean, if you don't know, well, A is going to be 10. Right, therefore, right, B is going to be 11. Yeah, D is going to be 12. C is 13. Right, so E is going to be 14. Yeah, which is this here. And then, if we look at these 4 bits, well, this is just 3. Okay, so that should just be E3. And of course here you would actually want to give your working space. So you can probably say something like, 1, 1, like this. Right, this equals 14, which equals E. And we can be more specific, right, where we say this in base 2 is equal to 14 in base 10, right, which is equal to E in base 16, okay, just to be more explicit. And then of course, we can do the same for 3 if we wanted. Right, then logical shift of 2 places left is performed on the binary number stored in the register. Okay, so yeah, we just want to do that shift. And if you think about this, well, if we're shifting 2 places to the left, then it means these 2 are going to get, shifted off the side. So that means, our new number is just going to be this, okay, but then we're also going to have 2 zeros that come in from the right. So yeah, so like 1, 0, 0, 0, right, 1, 1, 0, 0. And if we just write that, so I think, what was it, right, 1 and then 3 zeros, and then, yeah, 1, 1, and then 2 zeros. Okay, that should be correct. Right, the negative denary number minus 99 needs to be stored in the register. Complete the, okay, right, so yeah, using 2's complement, just represent this in binary. And I mean, there's a few ways we can do it. I'll try and demonstrate 2 ways. Now, the first way, we can just write out the positional values. So we can go, right, minus 1 to 8. Because since we're using 2's complement, the first position is negative. Right, then 64, right, well then 32, yeah, 16, 8, 4, 2, and 1. So because this is negative, of course, we need the minus 128. And then we need to think, well, how many positive numbers do we need? Or, yeah, kind of what positive sum do we need? And we can kind of think of that because we want to say, well, minus 128. Right, then plus n is equal to minus 99. So if we rearrange this, I mean, basically what we see is, well, we want to add, I guess, 29. Yeah, so we want to add 29, and that'll get us to the minus 99. So in order to get positive 29, well, there's going to be no 64, no 32. Right, there will be a 16. Okay, there will be an 8. because this gives us 24. Right, then there will be a 4. Okay, this gives us 28. And then yeah, so like this. I think that should be fine. Right, and I mean, we can also check this, of course. So we go minus 128, right, and then plus 16. So that's going to be minus 112. This is going to be minus 104, right, minus 100, and then yeah, minus 99. Okay, so that's of course fine. And obviously, well, you know, when it comes to the answer, right, just yeah, write your answer down here, right, in the answer box. I'll also show you the other way to do it, and this one, yeah, I mean, maybe it's going to take up a bit more space, but the way you can do it is if you write 99 positive, right, then you just want to flip the bits and add 1. So in order to write, and I mean, let's maybe go down here. So let's say positive 99. Well, what that's going to be, right, no 128s, but there will be a 64. Okay, there will be a 32, because this will give us 96. Right then, well, there won't be a 16, there won't be an 8, there won't be a 4, but there will be a 2 and there will be a 1. Yeah, I think that should be fine if I've made no mistakes. Right, then we just want to flip them. And flipping them will actually give us the 1's complement. Although, yeah, I think that's just for A level, actually. Right, so then let's just go here like this. So again, well, flipping 0 becomes 1. Right, flipping 1 becomes 0. Yeah, we're just inverting them. And right then what we want to do, we just want to add 1. And in fact, yeah, maybe actually let me erase this. Right, so to add 1, I mean, this one is actually quite simple because, well, we've just got a 0 at the end. But yeah, let's just write this out, right, to be explicit. And, you know, we can kind of like, I mean, let's just separate this, right, that's different. Because, yeah, we're just doing it on these two here. Right, so in order to add 1, well, here then we get 0, right, 0 plus 1, that's just going to be 1. And then, of course, we just got all zeros, so it just stays the same. Right, because, yeah, basically, well, what we've done, right, is, you know, we've done this thing here, right, and then plus 1, okay, and then that's going to give us this. And if we check, that should be the same. Right, so 1, 0, 0, 1, and then, right, 1, 1, 0, 0. Yeah, okay, which is the same as this. All right, so both of those methods work, right? It just depends what one you're more confident with. Like, I would say this second method is kind of easier, but it is a bit slower, because obviously here all you're doing is just, well, you're doing the positive number, right, then just flipping, adding 1. However, if you're confident directly working with the negative numbers, yeah, then of course you can just directly do it, right, using the positional values. Alright, so then here we just want another addition. So yeah, the number this is added to this, right, add the two 8-bit numbers using binary addition. So let's go here, right, 0, and we'll just write these out. Right, and then we've got 1, 1, 1, right, 0, yeah, 0, 0, 1, 1. And make sure to line these up properly. I mean, in the exam, I'll probably, yeah, line it up a bit better. Yeah, with the graphics tablet, it's, you know, not always the easiest. Right, so here then, well, 0 plus 1, that's just going to be 1. Right, again, 0 plus 1, that's also 1. Okay, 1 plus 0, well, that's 1. Yeah, 1 plus 1, 1 plus 0, okay, that's 1. Right, 0 plus 0 is 0. Right, 0 plus 1 is 1. Alright, then here we get the first carry. So 1 plus 1, right, that's going to be a sum of 0, but then a carry of 1. And then here we have the same, right, so, well, 1 plus 1, or technically, right, 1 plus 0 plus 1. Right, so that's going to be 0, but then we do actually get the overflow here. So let's just write this. And I think I mean, usually for overflow, we just put that in brackets, because basically this overflow is not going to be included. Right, yeah, this is actually the answer, just this one. But I think they do like us to show the overflow. Yeah, just so the examiner can see that we've kind of, you know, well, yeah, that we've actually kind of, you know, included the overflow in our calculation. Although, yeah, the answer, again, should just be these 8 bits, all right? Right, so 3, a user's computer has a central processing unit CPU that has a clock speed of 2 gigahertz. She wants to change it to a CPU that has a clock speed of 3 gigahertz. And I mean, giga, like, hopefully people know, right, giga just means billion. I think certainly, like, if you do physics, right, you should know this. Right, so state what is meant by clock speed. Right, so I'm going to type this. Okay, so what we can say then, clock speed, this is going to be the number of times the clock ticks per second, and on each clock tick, right, well, one instruction will be executed. So let's try and write that. Alright, let's say, well, clock speed is the number of times right, the system clock, let's say, ticks per second. Alright, and then, so yeah, this is kind of what it is, and then we'll say what happens on each tick. Right, so on each tick, right, let's say, yeah, one instruction is executed. Right, and let's say, yeah, executed by the CPU. Okay, right, so then we want to explain the change this effect will have on the performance of the CPU. So, I mean, hopefully you know that, well, if we increase the clock speed, right, because we're doing one instruction, you know, per clock tick, then if we're having more clock ticks, well, then that means, you know, more instructions are going to execute in that 1 second. So yeah, let's just try and write that out. Let's say, right, increasing the clock speed. Let's say, right, means the, well, I mean, yeah, it means there's going to be more clock ticks per second. Means there will be, right, more clock ticks per second. Right, and let's say, well, since, and I mean, like, some of this is kind of just restating the obvious, but again, I think it is better to include too much detail, and yeah, kind of, you know, just restate the obvious, like, rather than just thinking, well, the examiner is going to know this already, and, you know, just don't include it. Because yes, sometimes they do give you marks, you know, for saying like really obvious, you know, seemingly kind of stupid things. Right, so increasing the clock speed means there'll be more clock ticks per second. Right, yes, since an instruction is executed an instruction is executed, right, on each tick. Yeah, this means that yeah, more instructions will be executed per second. Right, executed per second. Right, and then, well, we can say, yeah, hence, right, hence meaning the CPU will be faster. Yes, maybe CPU performance will be faster. Yeah, I think that's okay. Right, the CPU contains a memory address register, or MAR, and we want to describe the role of the MAR in the fetch-decode-execute cycle. Right, so what we can say then, the MAR, right, well, this is going to hold the memory address that you're about to read from, yeah, or that you're about to write to. Right, so the MAR, yeah, holds, I mean, let's just write that, holds the memory address, right, that is about to be read from, yeah, or is about to be written to. Right, I think then we can be more specific, so we say during the fetch stage, right, during the fetch stage, because we want to think, well, this will be the memory address, you know, of the instruction we're about to execute. Because if you remember, well, this address is copied from the program counter, okay, well, into the MAR, right? The program counter can then increment. We say, so we say the instruction, right, at the address in the MAR is then copied into the MDR, right, the memory data register, and then while the contents of the MDR are then copied into the CIR, right? So that will be the fetch stage. Yeah, then that instruction can be decoded. And once it's been decoded, right, then it can be executed. And what decoding means is, well, maybe I'll demonstrate in a minute, but basically just kind of separating the instruction into the opcode and operand, and then yeah, just kind of the control unit will then send signals, right, to the correct component to actually execute that instruction. So yeah, I'll demonstrate that in a minute. Right, so during the fetch stage, right, let's say the MAR will hold the memory address, right, of the instruction that we are, and yeah, don't worry about spelling, right, instruction that we are about to execute. Yeah, that's fine. So I mean, let's try just to explain this decode part, because I think, yes, some people don't really know what decode means. Now, let's say, and I think actually the next one, I mean, yeah, so okay, let's do this one because this is related. Right, the CPU has a list of all the machine code commands it can process. Right, state the name of this list of commands. So I mean, well, this here is just going to be the instruction set. And yeah, I will just show you this on the assembly website. Right, so the instruction set, this is just a list of all of the assembly instructions. Okay, yeah, let me load up this assembly website. Okay, so now we can see this is loaded, and if we see here, right, this instruction set, well, this just gives us all of the list of the instructions. Yeah, so the assembly instructions. And let's say, for example, here we see, well, maybe LDD, right, or yeah, this add B. I mean, let's just go back and try to explain this. Like, let's say, for example, that maybe add, right, let's say add can be the instruction, you know, it's like 0001, right, so instruction 1 or something. So if we have the instruction like this, 0, right, like that, and then maybe let's just go 7. I mean, because you've got to think, right, this will all be stored as like 1 byte. So yeah, it's going to be stored together. Right now, what the control unit will do during the decode stage is, I mean, you can think it's kind of going to separate this, and then it's going to say, well, what instruction is, you know, 0001, okay, and it's going to look at its, you know, lookup table, right? It will then realize that's an add instruction, okay. Then it will think, well, what does this, you know, 0111 represent? And of course, well, that's just going to be the binary number 7. Now, you can of course also have different addressing modes. So rather than saying like add the binary number 7, you can also do something like you know, add the data. Well, let's say, right, add the data from the address 7. And in that case, you know, you'd have to have a different addressing mode, right? So you'd probably have these first bits would have to be different somehow. So I mean, yeah, this is a simplified version, right? But I mean, what the decoder is going to do, what it's going to figure out, right, what instruction you're executing. It's going to figure out, you know, the value of the operand and, you know, the addressing mode, right? So are we using immediate addressing, which means the actual value, right? Are we using direct addressing, which means, you know, kind of, well, loading something from a memory address, storing something in a memory address. Yeah, there's also, you know, what sort of indirect, right, relative, indexed. But again, that's going to be A-level content. All right, so the next one, and yeah, did we finish everything? Yeah, okay. Right, a washing machine is an example of an embedded system. Give 2 characteristics of an embedded system. Right, so here, yeah, let's just type again. I think first we can say it's going to be programmed to have a specific task. Right, programmed to, yeah, have a specific task. Right, okay, and let's say, yeah, the behavior can easily be modified. Right, can easily be modified. Yeah, by a sort of end user. Yeah, by end user, right, slash, you know, malicious third party. Right, and I think here we can also probably say it has dedicated hardware or, you know, specialist hardware. So maybe, yeah, say, right, contain dedicated slash, yeah, specialist hardware. Yeah, all right, and let's say, you know, e.g., right, so that'll be a microprocessor. Right, we can also say, you know, input-output devices. Right, there's going to be memory and also storage. Yeah, so I think that should be okay. Yeah, I think that's fine. Right, so the next one, we want to circle 3 other examples of an embedded system. Right, so this one I did actually have to check the mark scheme before, because I mean, I think sometimes they've said a smartphone or just a phone is an example of an embedded system. But yeah, I think in this case they actually don't. Right, so here then we've got to think, well, an embedded system is going to be a device that kind of has a computer built inside, right? But, you know, it's not, well, you can say that, you know, its kind of main purpose is not a computer. Or yeah, you know, it's not really a computer itself. So some of these we can instantly discount, right? Like a laptop. Well, a laptop is a computer, so yeah, that means it's not an embedded system. Right, likewise PC. And I guess these days, right, that's why they also say smartphone, because I mean a smartphone is basically just a mini computer. Right, so then we want to think about these, you know, which of these are going to be an embedded system. So I think we can also probably say that a web server wouldn't, because a web server, I mean, you can basically just, you know, take a web server, you know, install, say, Windows or, you know, any like Linux or Mac or whatever onto it. And I mean, pretty much you could just use that as a regular computer. You know, if you were to like plug in a mouse, a keyboard, you know, probably, yeah, some sort of screen. Because, yeah, a web server, again, it's going to have, well, it's going to have, you know, sort of powerful CPU, it's going to have like RAM, it's going to have, yeah, storage. So yeah, this is probably a bit too advanced really to be considered an embedded system. But then if we look at the others, I mean, a freezer, Well, this will have input output because input can be the temperature sensor, right, the thermometer. Output, I mean, this can be the thing that changes the temperature. So I guess kind of the like freezing panels, the cool panels at the back, right? I mean, it's also going to have a microprocessor because it needs to kind of it needs to perform an action based on the temperature. So if the temperature is too cold, well, then it can maybe turn down these sort of freezing panels. Yeah, of course, if the temperature is too hot, well, then it can increase the freezing panels, right, make them cooler. Yeah, likewise, it's going to have storage because it needs to store the actual value, of those. I mean, yeah, or well, it's going to have memory at least, right? It can like temporarily store, yeah, sort of temporarily store the values, of the previous. Yeah, I mean, I guess, well, maybe it will store the previous temperatures, although it doesn't really have to. All right, so let's circle this. I mean, again, likewise, the security light system. I mean, if it's just talking about a simple sort of camera, maybe it wouldn't. But in this case, because it's saying system, I mean, this sort of gives the impression that they're all sort of connected together, right? Probably there's going to be some kind of alarm, maybe they're communicating over a network. So yeah, in this case, again, this will have memory, it will have a processor, or yeah, microprocessor. It is going to have input output, because well, input will be, I guess, the sort of camera, and then yeah, maybe the output might be some sort of alarm or some sort of notification it's going to send, maybe to someone's phone or something. And yeah, likewise, vending machine. Well, input, obviously, yeah, the buttons. I mean, output, well, it's obviously going to have an actuator to push out the product. And of course, it's going to have a processor to calculate the price. Right, it's going to have memory. For example, well, memory or storage to store how many items remaining. Right, maybe it will store some sort of statistics, about the number of sales, right, things like that. Right, so 5, a band is recording their new song. They need to consider the sample rate and sample resolution of their recording. Give one benefit of using a higher sample rate to record the song. Right, so let's try and draw this quickly. So again, you can think of sound as like a sine wave. Okay, and then what we want to say, well, the sample rate, and actually let's change the color. I mean, the sample rate is just going to be, well, how often we're sampling. Well, yeah, how often we're taking a measurement. So let's imagine we're taking a measurement here at 0. Right, maybe we also take another measurement here, another measurement here, right, another one here. And these measurements, they should be like equally spaced because it's going to be periodic, okay, the sample rate. Now, if we think about this, right, let's imagine we're then, well, we've got a sampling resolution. And the sampling resolution is how many bits we're using per sample. Now, let's say here we're storing 0, this can be what? Okay, yeah, what happened? Right, that can be 1, right, maybe, well, in fact, I mean, yeah, let's have less, right, just to make it more obvious. I mean, let's say, I don't know, maybe this is 1, right, this is 2, this is 3. We can also have like -1, right, -2. Now, I mean, here this is fine because, well, the amplitude is 0, and we're also sampling here at 0. Okay, so yeah, here we just sample at 0, that's fine. But then if we get to the next one, well, I mean, the real value is, let's say, here. And I guess, I mean, this is quite accurate. This is probably like 0.9. Obviously, it's not perfect, right? But, obviously, of course, right, this has got to be stored as 1 because we can only store 0, 1, 2, 3. Right, if we get to the next one, well, this next one is kind of like, what, -1.2. And again, well, of course, this is closer to 1, right? So we then have to, closer to -1. So we'd have to store it, yeah, -1. Right, the next one, I mean, this is kind of like 1.8, I guess. So yeah, I mean, let's just store this. I mean, actually, that's quite close to 2. Right, this is actually not the best example because they are actually quite close to the real analog. But I mean, let's just think about this, right? So if we were to actually draw this, well, it's then going to be something like this. And yeah, obviously, right, kind of, etc. So you can see here that, this red, like, digitized sample, okay, this is nothing like the original analog sample. Whereas if you imagine, and let's use a different color, maybe green. Let's say, for example, yeah, we were sampling here at 0, but we also sample here, we sample here, sample here. Right, so if we have, lots of samples, right, so a high sampling frequency or a high sampling rate, well, then the actual, then the actual kind of digitized wave that we get is going to be, well, it's going to much more accurately, represent this original analog wave. right? And especially if we also increase the sampling resolution. So rather than just having like 0, 1, 2, 3, right, we have, 0, 1, 2, 3, and obviously, like hundreds of different values. And I think like a typical sampling rate is usually about 24 bits for high quality. Maybe 32 bits as well. So you can think, well, 2 to the power of 24. That's going to be, that's going to be a lot, because if we think 2 to the power of 32 is like 4 billion, I think about 4.2 billion. This is also going to be millions. And I think actually, this is like 16 million, right? Because that's how many colors there are with 24-bit color. Right, so to actually explain this in words then, give one benefit of using a higher sample rate to record the song. Well, we can just say that the audio quality is more accurately going to match the original, the original analog signal. So let's say the stored, or we can say maybe the stored / sampled, digital recording, will more accurately. And it's good it recommends that. More accurately represent the original analog, and I guess let's say wave. That should be fine. One drawback of using a higher sample rate. Again, if we look at this diagram, well, obviously each sample is going to be more data, because for every sample, well, we're using the number of bits, defined by this sample resolution. So of course, if we've got 1 million samples, well, that's going to be a bigger file than if we've only got 1,000 samples. Let's say the file size will increase. And then we can say, hence we'll use more space on the user's computer. Hence we'll use more, space. Let's say, on the user's device. And you could also mention kind of like sending it is going to be slower, right? Because it's going to use more bandwidth, right? It takes longer. So then what is meant by sample resolution? So as we've said, and actually this one is 2 marks, so we do have to describe this, right? Have a bit more detail. This is let's say maybe the sample, or the sampling resolution. So this is the number of bits for each sample. The number of bits used to sort of record or represent each sample. And then we can probably say that having a higher sampling resolution, as we see by this chart, we can see that the difference between the actual kind of individual amplitudes is smaller, right? Because if we just draw the scale, like if we have one let's say this is our value of 0, and maybe this is 1, right? Well, obviously here, like there's a big gap, in the actual amplitude value. Whereas let's say instead we're storing, we've got all of these values. Well, of course, the actual real amplitude is going to be like closer to the original analog sound. Let's just try and extend this. Let's say, hence, increasing the sample resolution means that the amplitudes, or maybe let's say the difference in amplitudes that can be stored will be smaller. That can be stored, will be smaller. Because, rather than only being able to represent, say, 50 decibels or 60 decibels, we could represent 50, 50.1, 50.2, 50.3, much smaller intervals. This you can also call quantization levels. Right? So quantization levels is the name for the sort of quantity that we have to round either up or down to. I think that's fine. And then you can also mention that increasing the sampling resolution means the difference in amplitudes will be smaller. And let's say as well as we can say the maximum range, or let's say as well as the range of amplitudes. Amplitudes that we can represent will be bigger. Right, because again, let's say we have a low sample resolution, well, maybe we can only represent between like 50 and 70 decibels. But if we have a high sampling resolution, we could represent between, I guess, you'd always want 0 decibels, to be honest. We can represent from 0 to like 100 or 120. Yeah, that should be fine. Right, 6, the table contains descriptions about data transmission methods. Right, yeah, complete the table. Right, okay. So the first one, data is transmitted down a single wire. Right, single wire, 1 bit at a time. So, I mean, well, let's just try and draw them. Right, so the different types we've got is serial. So serial means we've just got 1 wire. Right, then we've also got parallel. Right, so parallel, well, that's when we have multiple wires. So let's say serial, we send 0, then we send a 1, then we send a 0, right, then a 1. Whereas let's say with parallel, we can send a 0, 1, 0, 1, right, and we can send them all at the same time. Right, the next type, when it then says in one direction only. Right, so then we also have simplex. Right, simplex. Now simplex is if we can only send in one direction. Right, then we have half-duplex. Right, now half-duplex, this is if we can send in both directions, but not at the same time. Right, then we have full-duplex. And okay, I mean, yeah, probably but full-duplex means we can send in both directions, okay, and we can send in both directions at the same time. Right, so if you know these questions, they shouldn't be that difficult, as long as you read them carefully. Right, okay, so here then, down a single wire, well, that means it's going to be serial. And then, right, in one direction only, so that's going to be simplex. Right, yeah, so serial, simplex. Right, the next one, data is transmitted down multiple wires, multiple bits at a time, right, so that's parallel. And then it says in both directions, but only 1 bit at a time. So both directions, 1 bit at a time, right, that's this half-duplex. Right, so parallel, right, half-duplex. Right, data is transmitted down a single wire, okay, so serial, yeah, 1 bit at a time. Right, in both directions at the same time, so, right, that's going to be full-duplex. Right, the next one, data is transmitted multiple wires, right, parallel and multiple bits at a time. Right, but in one direction only, so, right, that's going to be simplex. Yeah, okay, so they should be fine. Right, the next one, a train station has a ticket inspector who checks each customer's ticket before they are allowed to get on the train. The train station wants a system that will allow the tickets to be automatically checked. Right, identify 2 suitable input devices that can be used to automatically read the tickets. Okay, so I think here we can think the different kind of code types. Right, so one is going to be a barcode. So then to read that, we can say, barcode scanner. Right, I think we can also think QR, right, so QR code, maybe let's say QR code scanner. And I think here you can probably also say camera, but I think it's probably better to say these barcode scanner, QR code scanner, because, they're a little bit more specific, right, whereas, I mean, a camera, yeah, I guess, I mean, you can use a camera as a scanner, but, I mean, that's not really the main use of a camera, right, obviously these scanners are going to be more kind of, more, built for that purpose. So I guess barcode scanner or, also reader, right, barcode reader. Right, the train driver pushes a button to close the train door when all passengers have boarded the train. The train door will only close when there are no passengers in the doorway. The system to check that there are no passengers in the doorway uses a sensor and a microprocessor. Explain how the sensor and the microprocessor are used to check whether the train door can be closed. Right, okay, so I think, I mean, the way this works then, I mean, probably you're going to have some sort of infrared sensor. I mean, you can probably say like a proximity sensor. But let's say here, right, I mean, this is like the left door, right, this one is the right door. So let's say this is going to be some infrared emitter, right, so this is going to send out some infrared signal. And then, I mean, maybe here they just have a detector, right, I mean, or possibly it might be reflected back, I'm not really sure. But I mean, let's say here it's probably just a sensor. So yeah, let's say that, let's say we don't need this thing. Right, so what's going to happen then is, well, in a normal situation, let's say this has a reading of like 100, right, so the strength of the signal that this sensor detects is 100, right, but if suddenly you've got a person in the way, well, now this person in the way, like maybe most of this infrared gets blocked out and, the signal goes down to 20. Well, obviously in this case they can detect, right, something or someone is in the way. Because, the amount of actual infrared being, detected by the sensor is decreased. right? So I think that's how that's going to work. And then you want to explain, how the microprocessor is going to use this to like either shut the doors or open the doors. Right, okay, so let's type this one. And if you look at the mark schemes, a lot of these sensor questions, right, they always look for the same keywords. So if you practice, 3 or 4 of these, then hopefully you should start remembering the mark scheme. Right, so I think one thing they often say, you can say, well, the sensor will continuously detect. So let's say maybe, right, I'm going to write this in bullet points, although in the exam you should write in paragraphs. But yeah, I'm going to use bullet points, right, just for speed. So let's say, right, an infrared, maybe, right, let's say maybe an, right, so an active infrared sensor, maybe emitter. I think sensor is okay. And so, we could say sort of infrared, right, / proximity sensor. That should be fine. Right, will continuously measure. We can say like continuously measure the sort of infrared levels received, right, or if something is blocking. Right, so continually measure the infrared levels received. Right, so this this signal will be passed through a right, okay, so hang on. Passed through an ADC. Right, so that's going to be analog to digital converter. Right, so let's say, right, the digital signal will then be used by the microprocessor. We can say maybe the digital value, right, will be used, let's say used by the microprocessor, right, and compared against sort of an expected value. Let's say, an expected value of, infrared levels. Or we could just say unexpected, infrared level. Right, let's say, if the infrared level is too low, right, let's say, this means something is blocking the doorway. Right, and then we say, right, hence the microprocessor, will use, right, let's say it will use a DAC. Right, so that's, digital to analog converter. Right, and send a signal. And then, here then it's going to send a signal to an actuator. And I guess, this can mean, just like don't close the door, or maybe to open the door, stop closing the door. Right, send a signal to the actuator to stop closing the door, or sort of like don't close the door, or I guess we could say like reopen the door maybe. Right, and then let's say however, right, however if the level is normal, if the level or reading is normal, and let's put in brackets, no obstruction. Right, obstruction. Right, then we say, the signal to the actuator. Right, we can say the signal to the actuator will be to close the door. Alright, so is that all they want? So, right, we've talked about a sensor, we've talked about the microprocessor. I think that's fine. And I mean, often like they love this word continuously, because it's not just going to detect once, because like maybe there's someone in the way, right, but then of course they move out of the way, right, so that's why it has to like continuously check. But I think we've mentioned that here. So I think, hopefully that should be enough for 6. But again, a question like this, definitely check the mark scheme. Okay, make sure you get everything that they have. Right, the next one, so draw and annotate a diagram that demonstrates the cybersecurity threat of data interception. Right, so this one is a little tricky. Here let's just start with a client. So let's say maybe client, or we can just say like us, right? And let's say, we can just say server, or we can call it receiver. So the client, you could also say, sender, right? The server, you could call receiver, it doesn't really matter. So let's try and draw something where, while the client is sending data, let's just say like traffic, or we could say packets, right? Packets or traffic. And let's say in here somehow, right, so let's draw this. And here you can just say like hacker or, malicious third party. Or let's say, malicious third party. Right, third party. And sometimes they do also call this a packet sniffer. Right, packet, with a K. And what a packet sniffer does is, it's just going to sniff the packets. So what that means is it's just going to detect the packets, right, intercept the packets that are being sent. And this could be over a wireless network, right? It could be over over like a fiber optic or Ethernet. Twisted pair, right, cable, something like that. Okay, and here, maybe we can just mention, like data interception or packet interception. Right, that's where this is occurring. And I think that's fine. Then we can also like draw the server responding back. And I guess, let's also say here as well, right, so it can intercept on the, kind of on the outbound journey, right, but then it's also going to be intercepting, right, on the inbound journey as well. Or we could just draw a kind of double-ended arrow like that, right, that's also fine. And then if we do the double-ended arrow, then we wouldn't need this. All right, so let's just erase that. That's fine. Like sometimes they also draw it like this where, let's just do it quickly, right? So client, then the server, right? And then let's say here, well, this is, let's call them H, right? The hacker, the malicious third party. So obviously, the client should be sending to the server, but let's say, somehow their connection has been intercepted. And obviously, while they're sending to the hacker first, kind of unknowingly, right? This hacker is then sending to the server. The server is then just responding. But because the hacker is now using its IP address, because it's changed the IP address of the packets, or it's changed the source IP address in the packets, right? From the client's IP address, and now it's put the IP address of the hacker. So the server is then just going to respond directly to the hacker. We can sort of draw that going back, right? And then the hacker can then just forward it back to the client, like possibly if they want. Often they would actually want to forward it back to the client. And the reason for that is because, from the client's point of view, this is completely normal behavior. They're sending packets, right? The packets are reaching the server. The server is, correctly handling that request. And then the client is, finally receiving, those kind of valid packets, right, from the server. The advantage from the hacker, the advantage in the hacker's point of view is that because the client doesn't know that anything strange is happening, they're not going to stop communicating, they're not going to investigate, right? To them it's completely normal. Whereas let's say, for example, if we just erase, or maybe if we just cancel this. So if we say here, if the hacker is not forwarding these packets back to the client, well, then the client will think, well, why am I not getting any data? So obviously they'll investigate, they'll stop sending packets. Whereas if the kind of if the behavior appears completely normal, well, then the client will just carry on kind of naively, and the hacker will be able to get more data. Right, so then we want to identify one security solution that will keep data safe from data interception and state why it will help keep the data safe. Alright, so this one is a bit tricky because you might think, well, we can just use like a firewall, but let's just draw it here. Okay, let's say we put a firewall here. Now the problem is, what if the malicious third party is inside the network, right? In that case, a firewall is completely useless. Even here, right? Even if the malicious third party is outside the network, if the firewall doesn't actually know that the malicious third party is outside, so the firewall will the firewall is just going to continue letting these packets through, right? It's not going to know anything. Possibly it might detect something strange on the inbound journey, but I guess, I mean, if it's a kind of sophisticated interception, then probably the firewall won't even be able to detect anything. Right, and then you can also say something like a proxy. But again, I mean, if we have a proxy, well, let's just draw here. Maybe so the client sends to a proxy. And then I don't know, maybe you have a hacker here, and then you have the server. But let's say, for example, the proxy kind of gets let's say the connection gets intercepted after the proxy, right? So then the proxy sends to the hacker, right? This one sends to the server, and again, this data is just going to go back, and from the client, this appears completely normal. But the hacker has actually positioned themselves, inside the connection, or somewhere on the wire. And I guess the hacker could also position themselves right before the proxy. Yeah, they would take the place of the proxy by say modifying the IP address, for example. Right. So here, okay. So I mean, the only way really to prevent against this is encryption, because encryption, well, the hacker will be able to actually, the hacker will get the encrypted data, but because it's encrypted, even if they have it, they won't be able to understand it. Okay, and I think, really that's the only solution we really have for this, which is not ideal because, again, the hacker will still get the data, but yeah, they won't be able to understand it. So let's see, right, encryption can be used. I guess we can say, maybe to protect the sort of anonymity of the data. I mean, maybe. Let's not use protect. Let's see, encryption can be used to ensure that even if the hacker can intercept the data, right, they won't be able to understand it. Right, they won't be able to understand it, without the decryption key. Now, obviously, I mean, if they have the decryption key, well, then they can just read everything. But like, if we're assuming that the kind of key exchange is secure, right, then hopefully this means, well, they wouldn't be able to read the data, okay, because they don't have the decryption key. So without the decryption key. All right. The next one, so right, okay, this table has descriptions about the internet, and we just want to complete the table. Right, the first one, the collective name for all the web pages available, so that's going to be the World Wide Web. And remember the difference between the World Wide Web, you can think of it kind of like as a Venn diagram, or maybe just a set, really, right, not really a Venn diagram. So let's say this is the internet, right, I'll just call it I. And then, well, the World Wide Web, right, www, right, that's part of the internet. Because if we think the internet, well, this is going to include, for example, email, right, this also includes, videos, so like video streaming. This is going to include all kinds of things like, let's say SSH, right, FTP, like various other protocols. Even things like, say, peer-to-peer, right, so things like BitTorrent, these protocols, right, that's also included on the internet. Whereas the World Wide Web, basically this is just, the collection of web pages that are accessed via, well, HTTP, right, or HTTPS. So it's, just a kind of sub part of the internet. Or you can say the internet is a superset, really. Right, so the next one, a small text file stored by the web browser that can store users' personal data. Right, so hopefully you remember this should be cookies. And there's going to be two types, right, session cookie and then also, persistent cookie. Right, so a session cookie, well, that only lasts, while the user has the browser open. As soon as they close it, as soon as they turn off their computer, right, the session cookie will be deleted. Whereas, the persistent cookie, this will stay for a given amount of time. Right, so let's say if the website says that, a cookie should last for 6 months, well, then that cookie will last for 6 months. Even if the user, closes their, turns off their computer, closes their browser. Now, the user can delete the cookie, and, deleting the cookies will actually delete the session cookies as well. So, when you, like, delete history, delete cookies, delete your, delete all of your, like, session storage. And cookies, you think about what they can store about personal data. So maybe things like settings. If you're using, like, different languages, I guess, it will store the setting of your language. For example, if you go to a website and change the language, right, it will then save that change. It could be things like if you're using light mode, dark mode, maybe your saved files. And yeah, I mean, it can also be like your account ID, right? So when you log into a website, well, the session cookie is going to correspond to like which account. And that's why if you steal someone's cookie, right, then effectively you can log in as that user. Because again, the session is just what kind of verifies, the session is, what's going to like authenticate the user effectively. Although there are, more advanced ways, like if you also check the IP address, check other things too, to prevent against this. Right, so the next one, uniform resource locator URL. Now, what this is going to do, what this is, we can say this is going to be a string that represents let's say the location, of a file on the internet. Right, so let's say a string that represents the location, of a file on the internet. I guess we can say, let's say on the internet, because the thing is, I think technically a URL doesn't have to be, like just HTTPS. You can also have other URLs which are I think one is just like, if there's like a torrent, right, it's going to be like a where you're going to have that protocol, and then when you click on that, that's going to say, right, do you want to open, and then it will open whatever torrent program you've got. Same with other files, right? You can get different protocols and then they'll open different programs. But anyway, okay, let's say a URL, this is if it's like for a website, right? So will contain and let's say a protocol, right? Then it's going to have let's say the domain name, right? Domain extension, and let's say also path, right? So path or file path. And to give an example of that, right, to give an example then, so let's say we have a website, the protocol is going to be HTTP, right, or these days mostly HTTPS, right, sorry, that should just be 2, right, just 2 forward slashes, not 3. Right, so this here is going to be the protocol, right, then the domain name, maybe let's just say Google, right, so Google is going to be the domain name, right, then the domain extension, right, that's going to be the .com, or .co.uk, .org, right, and then the path, that can be, I don't know, maybe index, or I think for Google, let's say something like maps, and then maybe you have some like query like, or let's say like latitude, and that can equal like, I don't know, 90.123, ampersand, right, something else, right, so then in this case, I guess here, right, this would be the path, and then here you say this is actually the query string. But the main things, right, so the protocol, right, then the let's say domain name, right, the domain extension, the path, and then let's say the query string, right, QS. Right, so actually not finally, right, the web server. So I think I'll say for this it's going to be the sort of software, or let's say hardware/software that's used to accept client requests and then provide a response. So let's say the hardware/software that maybe allows, right, clients to send requests, right, and will then let's say and will then do processing, before responding, with the sort of data/file, right, which it sends to the client, or I guess, right, let's say which it returns to the returns to the client, or responds with to the client. So I think that's fine. Right, then the last two. Right, so the language used to create a website example tags are head and body. Right, so this is just going to be HTML. And I think a lot of people may not know this because, I know, for example, on the Discord groups, a lot of people are saying, this is not included in the syllabus now. And I guess, sort of knowing, specific HTML tags is not included. And I'm not sure if that was ever included. I mean, maybe it was a long time ago. But I mean, they still do need you to know what HTML is, right? So, and then, I mean, the full name for this, well, hypertext. Right, so hypertext, right, that's going to be the H and then the T. Right, then the M, that's going to be markup. And then the L, well, that's just going to be language. And I mean, well, the hypertext markup language, I mean, yeah, that's just, this code, right, this, markup language. Right, the next one, a protocol that's used to request and send web pages. Right, so that's going to be HTTP, right, or HTTPS. And again, let's just write that. So again, it's going to be hypertext. Right, hypertext. Right, and then, well, okay, sorry, right, so hypertext transfer protocol. And then, well, the S, right, that's going to mean secure. Right, and obviously the S is optional, but these days, right, most websites are going to be HTTPS. Right, a business has a system that's described as having artificial intelligence. State one of the main characteristics of an AI system. Okay, so I think here for AI, we can say maybe it possesses, I mean, let's say, human-like intelligence. Or we can say, let's say, possesses intelligence. Or let's say, previously considered, only to exist in humans. Previously considered, right, to only exist in humans. Right, and then let's say, like, e.g., let's say, like, image recognition. Right, we can say sort of like language processing, or natural language processing. You can also say for like analysis, reasoning, maybe spatial recognition or kind of spatial awareness, right, things like this. So I think that would be the main characteristics. Right, then we want to explain how an expert system operates, and for this one I do actually have a diagram. Right, so here then we say, well, there's the user interface, and right, where is, okay. Right, so the user interface, well, obviously the user is going to interact with this. Now this could be a CLI, right, CLI, right, command line interface. It could be a GUI, right, so graphical user interface. It could also be others like, I think one, I'm not sure the exact name, but basically speech-based interface. Right, obviously, you talk to it and then it's going to talk to you. You can also have things like gesture-based user interface. So gesture, I mean, that's going to be, for example, like the Xbox Connect. And I mean, this is quite old, so maybe some people don't know what this is. Right, Connect. But I mean, this is also similar to, say, like, well, the Nintendo Wii, right, which, maybe people know, maybe they don't know. But I guess, I mean, this one is probably like 15 years old. In fact, actually, probably more, right? Probably about 18 years old, I would say, nearly. But I mean, what they would do is, well, they would have like a camera or, some kind of like device that you would hold. And then it would then use your movement to, control the character on the screen. Right, so that's why it's going to be a gesture-based or kind of movement-based interface. But I guess, I mean, for a kind of expert system, right, it's usually just going to be these two, right, just for a typical computer. Right, so, the user interface, well, you can use that to input data, right? I mean, then really it's going to go to the inference engine. And then what the inference engine is going to do, well, it's going to use this knowledge base, and actually you can see I think I've explained this before, it must have been. Right, so we can use this knowledge base. And the knowledge base will have a list, and well, let's say a list of facts, right? The example in the book is quite good, where let's say they have a list of animals, or they want to correctly categorize animals. So let's say we have a dog. Well, a list of facts, right, can be like 4 legs, or let's say it's a mammal. We can say, for example, can't fly. And then think of other facts. Maybe say it's got like hair, sort of hair/fur. So of course, you just have a long list of facts about dogs, right? That's going to be the knowledge base, right? The rules base, you can think of this as kind of like a tree. So let's say at the top, well, we just want to know what animal is it. So we kind of got a question mark. And then what we say, well, maybe the first question is like, is it a mammal? So let's say the answer for that is yes, right? And then of course we've got a no. Well, so then there's going to be another question. We say, right, does it have fur? So if the answer for that is also yes, and then obviously a no, right, a yes and a no, right? So you can see here this is just a tree. So you're just going to keep asking questions, right? You say, yeah, is it a mammal? All right, yes. Does it have fur? All right, yes. Can it fly? Right, let's say no. Does it have 2 legs? All right, no. Yeah, does it have 4 legs? Yes. And of course, eventually you're going to get down, and you're going to get you're going to get down to the root node. Okay, sorry, yeah, not the root node. You're going to get to the leaf node. Right, so yeah, where is that? Okay, here it is. So I don't know, maybe you have like a yes and then a no, right? And then of course eventually you're going to get down to the leaf node here, which is just going to say dog. And then of course now you know, well, yeah, this is why it's a dog, right? And then this is going to be used by the explanation system, because the okay, sorry. So yeah, let's say, well, the inference engine then, right? The inference engine is going to use the rules base and the knowledge base in order to arrive at the conclusion, right? And in this case, the conclusion is, yeah, the animal is a dog, right? Then the explanation system can kind of build on top of this, because it will then explain why it thinks the animal is a dog. And the way it can do that is where it says, well, it's a dog because, right, it's a mammal, right, which we see here. Right, because it has fur, right, because it has, because it can fly, because it has 4 legs, right, so it can basically use this tree, in order to explain to the user, sort of via the user interface, as we see here. It's just going to output why it thinks that, the animal is a dog, or yeah, why it thinks this email is spam, or yeah, why it thinks, this like growth is cancerous or not, or yeah, not cancerous. Right, and then not only is it going to explain what, but it's also going to explain, it's going to give a degree of kind of probability, right, or certainty. So it will say, yeah, I'm like 90% sure this is a dog, or yeah, I'm like 99% sure that this growth is cancerous. So yeah, I mean, basically then we just have to explain how this works. So what we can say, right, let's say, yeah, there will be. And again, I'm just going to do bullet points, but in the exam, okay, full sentences or full paragraphs. Right, so there will be a user interface, right, which the user uses to interact with the expert system. Okay. Yeah, I'll ignore the spelling. Right, so then we can say, right, let's say an inference engine. Right, an inference engine will then use a knowledge base. Let's say, right, that's a list of facts. Maybe we can say like about the chosen scenario, or about, yeah, or let's say about the system. Or let's say, yeah, the scenario that the expert system is knowledgeable about. Yeah, maybe has knowledge of. Right, let's also say, yeah, the knowledge base. I mean, I guess not always, but often it's kind of made by a person. Let's say, yeah, often made by a person. Yeah, or let's say a human expert, right? Because yeah, this is why it's called expert system, because yeah, often they're made by human experts. Right, so it's going to use a knowledge base, right? Okay, and yeah, also a rules engine. We can say this is maybe just say like a list of sort of conditions, right, or kind of if statements. Yeah, let's say a list of conditions to help. I mean, yeah, let's just say to help the inference engine arrive at the sort of conclusion. Yeah, arrive at the correct conclusion, or yeah, sort of prediction. Okay, I think that's fine. And then yeah, let's then just mention the explanation system. Right, an explanation system can then be used to explain. Right, let's say explain why the inference engine arrived at its conclusion. Right, yeah, and also right, give a degree of certainty, right, about its prediction. Okay, so I think, yeah, that seems okay. Again, with these 6 markers, check the mark scheme, right? Just check you've got everything that they have. And again, the mark scheme is honestly the best way to learn. Right, is this the last one? No. Alright, yeah, I mean, this paper has so many questions. Right, a manufacturing company uses an automated system in its manufacturing process. The automated system uses a flow sensor. Right, identify what a flow sensor measures. So a flow sensor, usually it's probably just going to be a tube, and then it's just going to measure how much gas or liquid, flows through that system. So let's just say, yeah, the rate of flow, of a gas or liquid. And I guess, we could let's put in brackets, right, amount, of gas / liquid, right, over a given time. Because, when you say rate of flow, well, rate of flow means the amount over a given time. But possibly in the exam, they might be looking for, this key term, over a given time, or, per unit time, something like that. And, they might also be looking for, this keyword amount. So I think, that's why you just kind of write both, both ways, say rate, right, and also, amount, and then given time. Right, explain one advantage to employees of using an automated system in manufacturing. So here then, this is a bit tricky because we don't want to talk about advantages to the company or to society, right? We want to talk about advantages, let's say for employees of having kind of like a robot colleague, right? Or well, in this case, an automated system, helping them, right, or assisting them. So I think you can say, right, the automated system can be used for dangerous tasks. Can be used to perform dangerous tasks previously performed by humans. Performed by humans. Hence improving the safety and job quality. Safety and job quality for workers. Or employees. I think that should be fine. And again, here it says only one, but if you did want to think of others, I think you can also mention some tasks are going to be repetitive, they're monotonous, maybe they're straining. Like physically straining, right, mentally straining. So in that case, you can have the automated system perform those tasks, and then the humans can sort of perform the tasks that, maybe require more dexterity, or more kind of let's say, thinking, like on the spot, kind of creative thinking, which, obviously an automated system is, probably not as good at. So explain one disadvantage to the company owner of using an automated system in manufacturing. Right, and again, obviously this is talking about the company owner, so you can't really mention, people losing their jobs, because I guess the company owner, well, in theory, they don't really care about that. They're just really focused on, making a profit. So the disadvantage, well, there's going to be a high, let's say high initial setup cost. Due to the maybe hardware purchase, or the automated system purchase. And also expertise, required to develop, / install, / maintain the system. Let's say, the automated system. I think that should be fine. Possibly you could talk about, like, maybe the automated system, I don't know, like maybe, for example, you have some product requirement that changes, and like rather than making a product in one way, you have to slightly change the design. Well, obviously an automated system is not really going to be adaptable. You've got to completely, build a new automated system, or you've got to completely, disassemble it, right, modify it. Whereas, of course, a human, you can tell them, right, we need to change the design slightly. And of course, the human can, easily do that. You could possibly mention, I don't know, maybe you could mention sort of safety issues. although that's not really an issue for the company. Yeah. Right, and I think for this one, I mean, probably also give an example. So you could say, right, for example, let's say mining, right, maybe like spray painting, because yeah, you often see things, you know, spray painting cars, right, spray painting, yeah, trains, planes, right, any sort of vehicle. Right, next one, digital currency can be used to pay for products and services. Digital currency is often tracked using digital ledgers. Right, give two other features of digital currency. Okay. So I will be honest. I mean, this one I did actually look at the answers. I think, yeah, I think maybe I looked at this paper a couple of weeks ago, because for this one, I mean, I would say, well, they're going to use a blockchain. I mean, yeah, maybe not always, but you know, here the digital ledger is just the blockchain. Right, now you can also have digital currency. Let's say, you know, PayPal. Obviously, other countries have their own versions. I mean, I guess some other ones that are known sort of internationally. Let's say. Well, let's say like, yeah, Google Pay, Apple Pay, or yeah, was it what, Google Wallet or Apple Wallet, whatever they're called. Yeah, I think Google Pay, Apple Wallet. You know, I think they're not really using a ledger. Okay, they're just using a more sort of standard, you know, simple version. But yeah, I think here they don't actually accept that. I think the answers they gave, right, so I think one, they said they're only, let's say, only stored / accessed, you know, well, electronically or digitally. Right, and then probably another one they give, yeah, I think I remember they said, so it can be centralized or decentralized. Now, again, in the case of like, well, PayPal and other kind of, I mean, let's say, you know, things owned by big companies that have more kind of, you know, legal obligations. So things like, you know, what Apple, like, yeah, what Apple Pay or Apple Wallet, whatever it's called, same as like Google Pay. You know, of course, because these are big companies, like they can't really just have some blockchain that, you know, doesn't record any personal details, because, you know, then when someone commits a crime, well, the police are going to ask, you know, like who is the person that, you know, bought this gun, right? Who is the person that bought these drugs? So in that case, right, for these big companies, of course, it has to be centralized, right? They have to store all this information. But for other digital currencies, let's say, you know, some cryptocurrencies, well, you know, the advantage of them is, right, privacy, yeah, kind of anonymity, which in that case, they can be decentralized. So I mean, let's just say, right, can be, yeah, centralized or decentralized. And I mean, this is a little bit strange, kind of, you know, as a point, but yeah, I think this is what they do accept in the mark scheme. Right, so then we want to identify the process that uses a digital ledger to track the use of digital currency. Right, so that's just going to be a blockchain. And I mean, just to recap kind of how the blockchain works, well, you have each block, and let's say here we have, you know, like transaction 1, right, transaction 2, transaction 3. Right, I mean, each block, yeah, each block is going to be a certain size. Now, maybe that could be like 100 transactions, right? It could be a size in terms of like megabytes or kilobytes. But yeah, right, it's going to have, let's say, a list of transactions, right? Then it can also have things like a timestamp, so like when the block was created, and then it's also going to have something like a hash code, or yeah, we can say hash value, right? Hash code. So like then when we get the next block, and let's say this hash code has the value, I don't know, like ABC. Yeah, okay, I don't know. In fact, probably let's not use ABC, let's use something a bit more random. So, I mean, let's say the data, well, I guess, I mean, yeah, I think ABC is fine, actually. Right, so let's say the hash code, you know, for this data, right, and, you know, when I say data, well, that can be a hash code of the whole block. I mean, probably not, well, yeah, not including the hash code itself. So, right, it's just going to hash the transaction to timestamp. And then obviously, well, then you're going to have, right, T1, T2, T3, but, you know, in block 2. And then what this is going to store, okay, this is also going to store, let's say, the previous hash. And then, I mean, what's going to happen is, because this is decentralized, right, I mean, well, in the case of, yeah, sort of in the case of, you know, cryptocurrency, it's going to be decentralized. But, I mean, the whole point of a blockchain is that, you know, people can verify, well, is this hash correct? Because, right, I mean, then people will check, well, they'll then recalculate the hash of, you know, this T123 and the timestamp. And if, for example, someone has modified this transaction, So maybe rather than sending 100 of whatever currency, right, they've actually modified it to change like 1,000,000 of this currency. Well, now, right, the hash value that the next people calculate might be like XYZ. So of course they can see, well, yeah, XYZ is right not equal to ABC is not equal to XYZ, right? Therefore, people on the network will know that this block has been kind of illegally or maliciously modified. So yeah, that's going to be the benefit of the blockchain, that you can detect modification. Okay. Right, and then I think the final one, so storage and memory are important components of a computer system. Primary storage is one type of storage in a computer system. Tick one box, right, which is an example of primary storage. Right, so the difference then between primary storage, if you have the CPU, right, let's just say, well, P, right, primary storage and secondary storage. Primary storage can be directly accessed or directly addressed by the CPU, right? So the CPU can, directly load. So I guess we can say, directly read and also directly write data to primary storage. Whereas from secondary storage, well, first the data has to go into primary storage, then it goes from primary storage into the CPU. So these we have to think, well, which one can the CPU access directly? Right, so I mean, it can access CD, okay, it can access the hard drive, but yeah, it can access the RAM directly. Right, so one characteristics of primary storage, well, let's just say, yeah, can be directly, maybe addressed or accessed, right, by the CPU. Yeah, okay, I think that's fine. Alright, then the last one, so virtual memory can be created in a computer system. Right, yeah, complete the description about virtual memory. Right, sometimes will not be used and sometimes will be used more than once. Right, so, I mean, if we just think about what virtual memory is, okay, before we have a go. I mean, virtual memory is where, well, if you have the RAM, okay, the RAM gets full, and then what you do is you then use secondary storage as a temporary, basically as a temporary, main memory, right, or temporary RAM. Because let's say your RAM has like 8 gigabytes, but you need 10 gigabytes of actual sort of programs data in RAM. Well, of course, yeah, here you can store 8, right, but then you can also store an extra 2 gigabytes here, on your secondary storage. And then when you need, right, this data, well, then you can like swap it back into RAM. Okay, but then of course it means, well, something in RAM has to get swapped out. So yeah, this obviously it's good in that you can use more RAM than what you have sort of by default, but this will also be slow because you've got to think, well, RAM is going to be significantly faster compared with secondary storage, and especially if your secondary storage, right, or your virtual memory is a hard drive, because yeah, hard drives are going to be much slower. Right, so let's try and complete this then. Virtual memory is used when the something is full, right? So as we said, right, this is going to be the RAM is full. And of course, yeah, you can write this, but I'm just going to draw arrows. Right, it is created by partitioning the something. Right, so that's going to be, I guess, hard drive. Yeah, that seems the most reasonable one here. I mean, more generally, you'd say, created by partitioning the secondary storage, because it could be a hard drive, it could be an SSD. But yeah, I guess in this case, right, they only list hard drive. Right, data is divided into something that can be sent from something to the something to be temporarily stored until they're required. Right, so when it's talking about RAM being divided, I mean, like RAM is not just one big, 8 gigabyte sort of block. Right, basically RAM is going to be broken down into pages. And each page is going to be about 4 kilobytes usually. I think 4 kilobytes is the default page size. So you can think, well, if you've got 8 gigabytes, how many 4 kilobyte pages are you going to get? Yeah, so it's going to be quite a lot, if you do that calculation. Right, so this is going to be pages. So let's just do that here. Right, so pages can be sent from something, right, to the something to be temporarily stored. Right, so here then again, and it does say we can use them more than once. So I think this one should be RAM again, right, because they're sent from RAM and then, well, to virtual memory. Okay, and virtual memory is just, well, the name for the portion on a hard drive, yeah, or SSD, that's used kind of to act as virtual memory. So yeah, that's going to be this one here. Alright guys, so actually this video went on a lot longer than I expected, because yeah, I think I was quite detailed with some of those descriptions. Now, I mean, hopefully that video is useful, because I mean, well, I know some people, they just go through the paper really quickly, but in that case, if they're not explaining anything, then really you can just use the mark scheme. So yeah, I mean, well, let me know, right, are the videos too long, or are they useful? And then yeah, I can also adapt them. Right, but as I've said, I mean, don't only watch the videos, right? Also use the mark scheme, because I mean, well, definitely there's things I forgot. But yeah, anyway, if this is useful, then see you again in the next video.